morning, everyone. I'm glad I sat through the previous talk, so I know how much out of place I am, but please don't blame me. I think the organizers wanted to introduce some kind of diversity. So if what I taught makes sense to you, well and good. If you think it's totally out of place, please feel free to doze off. I'm from IIIT, and some of my colleagues have spoken to you earlier, so you know about it. It's an institute in almost another city, electronic city, way off from here. And we have people working on several diverse fields, like we have web sciences, we have computer vision, we have NLP. So we have various fields of streams that are being pursued there. Okay. So I work on healthcare, computer vision, signal processing as applied to healthcare. So which is why Professor Uttam chose this topic for me. So when I saw the title of the workshop, I was wondering, how can I fit in healthcare in this kind of a workshop? And then I saw that satellites are indeed used in healthcare, but in a very different way. For example, they check the kind of ozone depletion that's going on, the air quality, the water cover, and things like that. So this is a very, very roundabout way of satellites participating in healthcare on a very different scale. And I also looked up some literature. Yes, satellite imagery is used to predict health. So I saw some recent papers from Stanford. So I was trying to get the confidence that it's not so much out of place. And maybe it could help with the current corona outbreak, but how? It's for you people to figure out. So I was seeing what are the kind of differences or similarities between satellite images and medical images. So this is an example of a natural image. It is for consumption, right? So we see how aesthetic it is, what information it contains. But when you look at medical images and satellite images, it's a very, very different world. So what it is conveying is on a very different scale. So the scale of the area that's mapped into the images, medical images, you'll want to cover every whereas satellite images, the range is in meters, kilometers sometimes. So we are looking at very different scales. But then, are there any unifying factors? I don't think so. In both the cases, we are looking at some kind of interpretability, right? So things are not obvious to us. We need to do something with the images to get the interpretation we are looking for. And there are different acquisitions possible. So the same field of view can result in different kind of images. So we need to put them together and arrive at what analysis we are looking for. So I was thinking, what could unify the two kinds of images? And both domains, they need data-driven approaches. You need to eliminate human bias, and you might end up discovering something that was earlier unknown, right? By having a data-driven approach. This, I think, is critical in both the fields, whether you're looking at satellite images or medical images. So at IIIT, we work on, this is the word that Shilpa was struggling with, so we call these fundal images. These are images of the eye. So we've done some kind of analysis on this, some simple things like extracting blood vessels, like extracting some landmarks. We've also worked on magnetic resonance images. MR stands for magnetic resonance. So we've looked at some simple problems like if there is a subject doing a certain task, what part of the brain gets activated? If there's a tumor in the brain, how do you detect it? So the last example you see, that shows you where all the activation is happening in the brain when a certain activity is performed, right? So these are the kind of problems we look at. And we also looked at some examples of 1D series. No matter what we are doing, there are always electrical signals generated in the brain. So this is just a representative diagram, and what is used to capture it is called EEG, electroencephalogram. So there are certain things we've done with it. We've tried to classify something which is normal, seen in several of us, versus something which is not normal. For example, the person could be epileptic, the person could be alcoholic. So how do you classify between the two? You can also study normal subjects. How does the brain function under different kinds of tasks? So the kind of problems we've looked at is when the person is doing a mathematical computation, how the signals look, versus if the person is under stress, how the brain looks, versus if the person is resting, how the brain looks, things like this. We've also done some kind of creativity assessment. You ask a person to draw a picture with lots of details. How do the signals look? Versus you are doing something monotone, just drawing tally marks or drawing some blocks. How do the signals look? And every activity carries its own signature, which is why we have been able to come up with schemes to distinguish them. So this was the setup of the EEG experiment. There is a person there wearing that skull cap, and all the circles that you see there, that's where the electrodes are picking up signals from the brain. That data is pre-processed, some simple kind of filtering, and then you extract some features, I'm sure just the way you do with satellite images, and then there is some classifier or some regressor, and then finally you get some interpretation out of it. Now, so that was what we do at IIIT. Now, a small overview of what our field is about. So I'll be covering some simple basics of medical imaging. We'll be looking at what are the possibilities, what does the community work on, and a little bit on causal reasoning. Now to start with, this is an image that was generated in 1895. Any guesses what this is? To whom does it belong? Mrs. Ronjan's hand, right? So this was the very first medical image that was generated way back in 1895. It was not patented, being used very well by everyone even now, right? See the ring on Mrs. Ronjan's finger. Yeah. And then we have images of red blood cells, right? You use electron microscopy. This is imaging of another kind, ultrasound. There's a baby sitting in the womb and you're trying to image it. So the objective of medical imaging is to measure a physical phenomenon, right? You want to assess a biological system, a living system, without perturbing it too much. That is the goal of medical imaging. It is imperative when you want to diagnose diseases. You don't want to cut open and then figure out that there was a tumor or there was no tumor, right? So you want to know it beforehand. And it's very important to understand the underlying biological processes. So what comes out of medical imaging could be a 1D signal, the way it is with EEG or ECG. It could be a 2D image, where it's a matrix of size some m cross n. It could be a 3D volume. For example, when they image our brain, it's a 3D volume, right? So you want the entire brain to be imaged. So it's a volume of size m cross n cross v. It's a 3D matrix. Can it be 4D? Yes. When you're doing a time series acquisition, you pick up a time evolving volume. So when the subject is asked to do a certain task, you want to see how the entire brain is changing as the person is doing the task. So then you end up collecting a time series of volumes. Now, what are the key factors when you acquire a medical image? You are looking at how good is the contrast sensitivity, how good is the resolution, both spatially and temporally. So we'll see what we mean by these. Now, image contrast. The word itself means how well can you differentiate something from something else, right? So when you see the panel on the left, you see that you cannot distinguish the region of interest, the circle that's drawn in the middle, very well from its background, whereas in the other case, maybe you can do it better. So this is what you want. What you want to image should be very distinct from everything else around it. So this is the meaning of contrast sensitivity. So you want a modality that gives you better and better contrast sensitivity, right? So that it's clearly visible. What you're looking for should be clearly visible. What is key here in making this happen? You should be able to translate tissue differences to image intensities. That is the key thing. Now we are looking at a cross section of abdomen. One is the CT image, the other is the MR image. So depending on what you're looking for, you will decide which of the two modalities is better, right? One image looks grainy, the other image looks not so bright. So there is no one choice. So depending on what you're looking for, you will decide which modality to go with. So this is an example of a brain image. Now I'm calling it low resolution because I have another modality which can give me something better. So what do we mean by resolution? The ability to have more and more details in your image. So a greater spatial resolution is very much desired. Why? Because you want to see more and more details in the image. So this was the spatial aspect. Same way temporally. When you are looking at a dynamic phenomenon, you want to have more and more timestamps, right? So what the rhombus marks, the square marks you're seeing there, so those are the timestamps at which data was acquired. But ideally you would want more and more so that you can study the dynamics better, right? What if you could have all of these blue ellipses? Then you could see what is happening at a much finer scale. So it turns out that higher temporal resolution is very critical, especially in things like cancer imaging. So overall, you will compare modalities as what kind of spatial resolution they give you, what kind of contrast resolution they give you, and what kind of temporal resolution they give. So you want to do well on all the three counts, but then no single modality can do that. So you want to have small numbers for spatial resolution, small numbers for temporal resolution, and very high contrast resolution. So you cannot have everything, which is why you need to fuse information coming from different modalities and then build up your interpretation. Now let's look at some of the possibilities and challenges. So what are the challenges you face when you acquire a medical image? So there are some things involuntarily that's always happening, right? We are breathing all the time. There is peristalsis, that is movement of food through the stomach. We have reflex actions. So all these come in the way of imaging, right? But nothing can be done about it. So we have to model it and make sure that we don't account for these in our images. And the kind of acquisition conditions, the patient could move, wherein you get a distorted image. The kind of contrast agent that is being used, the kind of hardware. I might have some low quality hardware, you might have something better. So the kind of images we'll end up with will be very different. There could be noise from the external environment, like there could be some electromagnetic coupling. So there can be a lot of diversity across images, even though the imaging intent may be the same. We intend to acquire the same thing, but we end up having different variations of it. So this is a huge challenge in imaging. And then come the processing challenges. There are lots of variations across subjects. Like as we know, each one is unique, right? So the same organ can look different in me, can look different in you. Differences across races, across age. We look different when we are younger. We will look different when we age. Attributes of the data, the signal to noise, the contrast to noise. So here, unfortunately, though we know that good SNR, a higher value of SNR is very important, when you want greater resolution, your SNR will drop. So you have to strike a balance between how to image it best. And some assumptions like spatial invariance, they may not hold when we are analyzing data. and even data availability, right? So when we are studying a disorder, the kind of data we can collect on that is severely limited. Fortunately, most of us are normal, right? And very few of them are facing that disorder. So the data sets always turn out to be imbalanced, and there are lots of machine learning challenges because of this. Annotated data sets can only come from experts, which means it is very expensive. Unlike natural images where everyone knows what is a cat, what is a dog, what is a table, here it's hard to tell what is a tumor, what is a normal tissue. Only experts can annotate. And there can be data sets where the expert himself says he's uncertain about it. So you have to deal with this kind of challenges. And the entire volume you acquire may be as big as 512 cross 512 cross 512. But the region of interest, the tumor that you're looking at, may occupy a very, very small fraction of it. So it's like you have to analyze a sea of data just to get a tiny pearl out of it. So it's highly imbalanced. So you cannot easily replicate the success that natural images have seen with computer vision algorithms. Now, we'll just look at some of the things that people in this community are working on. So there is this challenge, it's been from 2012. It's called multimodal brain tumor segmentation. So they present brain images with tumors which are acquired using different pulse sequences. You have to fuse all the information together and detect where the tumor is. So this is the challenge, and the community is working on it all the time. So this is the objective. Given the brain image, can you tell where is the tumor core, where is the entire tumor, where is the enhancing tumor, and so on. So you need to fuse information from the different images to be able to get to this. Besides, there is also this ADNI initiative. It's a very huge drive, very well funded by the US. It's on Alzheimer's disease. So they've put up data of different modalities. There is PET data, MRI, CT, you name it, and they have that sort of data. And they want people to come up with some inferences on how to prevent Alzheimer's or how progressive it is. Just about any kind of thing that you can infer on Alzheimer's. So for example, this paper discusses how you can classify patients with Alzheimer's disease from structural MRI. So apart from these, there are several ongoing challenges. There is also this cancer imaging archive where you have time series data. So there the key thing is to look at how the disease is progressing or how the therapy is working on a certain person. Is it doing well, not so well? And then the generalizability of algorithms. So typically you have algorithms for a particular anatomy. What works well for the heart may not well work for the abdomen, may not work well for the eye. So can you have some kind of generalizability across these algorithms? So that is this decathlon challenge. So when you look up literature, there are works that they report with very, very traditional features using texture, LBP. I'm sure you've heard of these local binary patterns, Gabor features, wavelet features. And they also use something very, very fundamental, some statistics based. Could be just mean, could be entropy, histogram, so things like that. So people have tried out a variety of features. These are handcrafted features in search of results. So apart from these, deep learning. So it's a part of the name of your workshop also. So people have used deep learning to analyze images. So can CNNs be used for segmentation? Can they be used for tumor segmentation? And so on. And last year around this time, this paper in Nature was a very popular one. Lots of authors, as you can see it. So they've reported that X-rays, they've looked at a huge volume of X-rays looking for certain disorders. And what they have reported is that their algorithm is able to do much better than the radiologists on certain diseases, right? So this challenge is still open. All this data is available for the entire public to work on. But in spite of all these success, the utility of AI in healthcare is severely limited. So what do you think is the missing link? I don't know how it is with satellite images. Do you still need an expert to give a nod, or you're fine with an algorithm telling you, okay, this is your land cover, this is your vegetation cover? Yeah? Explainability. Right. So this is where I think causal reasoning will play a very, very critical role in years to come. Now, causal reasoning in healthcare, all of us know when we go to a doctor with an ailment, we are asked a bunch of questions, right? So what did we observe? What made us approach the doctor? So based on the answers to those questions, he will have a sort of decision tree. Could it be because of this? Is the X-ray showing something normal? Is this test showing something out of the way? So there are a set of questions, and he's building a model out of that, right? So these are called DAGs, directed acyclic graphs. So one thing leads to another, and then there can be a fork, there can be another fork. So there is a proper hierarchy. So there are some parent nodes, there are some children nodes, and so on. So this is what the doctor builds in his mind. So he needs to make inferences from observations, right? And he will have a model for it. So it's very critical in healthcare because you want to treat the cause and not the symptom. So how do you come up with inferences from mere numbers? So what we look around us are all numbers, right? For example, if I want to answer a question like, let's say the MMR vaccine. So all of us have taken our kids to hospitals to get this vaccine administered. We know how important it is. But when you look at the data, it will show you that an estimated of so many kids, they fall prey to this kind of a thing. But when they are vaccinated, there is a chance that 1 out of so many will develop some adverse reaction. There is a chance that 1 out of so many, it will not work, and things like that. These numbers are very, very scary to look at. But this is all we have. So with these numbers, we have to decide this. Should this vaccination be recommended, yes or no? So from numbers, we need to build models. And we need to use those models to come up with the right inference. Another example, you look at a certain population, some of whom were vaccinated, some of whom were not vaccinated. And after some years have elapsed, you look into the number of people who died, the number of people who survived. And then you see something scary. Among the people who died, you see a certain percentage were not vaccinated. And among the people who survived, you see that almost a comparable number of people were vaccinated. So what's happening? So how do we come to conclusions? So this is the table from which I got those numbers. So I want you to look at, these are the numbers, you see, 73.6 and 70.6. So it looks like, is it making any difference? Should we go through that? Is there any advantage? So hard to come to any conclusion. What is coming in the way of our inference? So they are called the confounding factors. What could these confounding factors be? Apart from vaccination, there are a host of several other factors. Some genetic factors, some cardiovascular factor, it could be some diabetes, some BP. There are a host of other things also that have to be taken into account before deciding what led to greater survival or what led to death. Another example of looking at variables that correlate. So we tend to get confused between correlation and causation. So there was this paper that caught my eye. So when you want to analyze this hypothesis that storks deliver babies, you see how statistically significant it is. So P is 0.008. So you think that it is indeed true, but you know it defies common sense, right? So the unthinking interpretation of correlation and p-values can certainly deliver unreliable conclusions. This is what the author says. Just looking at the graph between number of births and stocks, you see the correlation is so beautiful. But then what are the confounding factors? The population of the country, the area of the country. So those are the factors that we didn't take into account while analyzing this. So when you look at a statistical dependence between two variables, one of the two can happen. Either X is influencing Y causally, or Y is influencing X causally, or there is some other factor Z which is influencing both. So this is one of the scenarios and this is the other. So how do you reason formally about cause and effect? When do you say that A is causing B? So how do you define cause and effect? So lots of philosophers have got into several arguments on what is cause, what is effect. So try to think in your own minds, when will you say that X is causing Y? So there is this causality theory developed beautifully by Julia Pearl. So the modeling of the underlying structures provides a language to encode causal relationships, and that is the basis of causality theory. It helps you decide when and how causation can be inferred from domain knowledge and data. So machine learning, as we knew some time back, was all about curve fitting. You just had to get the best line, the best straight line to model your data, or get the best boundary to separate between two classes, right? But machine learning, is it all about fitting the best curve? There's more to it. You need to explain the phenomenon. So that's where causal reasoning is very critical. So some of the limitations of statistics in understanding phenomena, I just chose a simple example. So when we have two random variables, say X and Y, here what is the event we are discussing? We are rolling two dice, right, X and Y. So they represent the probability that I get 1 on top or I get 2 on top, right? So that is the joint distribution table that we are seeing there. So that's why we have 1 by 36 for all of these pairs and so on. Hope you're getting it. Now, what is the basic understanding? Once I get the joint distribution table, I know everything about that event, right? That is what we know so far. So we believe every aspect of the situation can be inferred from it. For example, can I compute marginals? Yes. Can I compute conditionals? Yes. What more is there to be answered? Maybe there is more. Let's take up this example. I'm sitting inside a room with a barometer, and outside there is some atmospheric pressure, right? So what do I know? When barometer reading increases, atmospheric pressure increases. The other way around, when the barometer reading decreases, atmospheric pressure decreases, right? So are they both correlated? Yes. So if I know one, I can tell you what is the other, right? Now, let us say that currently the atmospheric pressure is at some A naught and my barometer reading is at B naught. What can we say about A naught when I read B naught? I can say that A naught comes from a distribution whose mean value is B naught, right? If I'm now reading 90, for example, then A naught could be 90.2, it could be 91.8, so somewhere around that. So that is what we think, right? So what we are asking here is, what is the probability that A takes on the value A naught when I observe that B equals B naught. So this is a conditional interpretation. But let's consider the following scenario. I nail the barometer to a certain number B1. I fix it. Now what can you say about A equals A1 knowing B1? Does the same interpretation hold? There can be a storm outside, and here my barometer can be showing that it is perfectly normal, right? So here A1 will not come from a distribution centered at B1. So here can I ask the question, what is the probability that A takes on the value A1 given that B is B1? Is this question fair to be asked? No. Then what is the question that we should ask? So in the first case, I just observe that B equals B naught. In the second case, I am forcing B to be B1. So the difference between the two is, in the first case I am just observing, whereas in the second case I am acting or I am intervening, right? So I have to consider these two scenarios very, very separately. So probability of A given B, the conditional is when you observe. But when you intervene, the question is semantically different. There the question you are asking is what if? So this is denoted by probability of A given that I am intervening on B. And intervening on B is represented as do. Do of B equals B1, which is where I am intervening, right? So in general, probability of A given do B equals B1 is not the same as probability of A given B. Now, but what is probability of A given do of B? What is the difference? I should be able to compute what is probability of A given do of B. So we are trying to answer this. How do I estimate this? When I intervene on a variable, how do I determine the distribution of some other variable? What is the connection between intervening and observing? So here is the man we spoke of, Julia Pearl, the pioneer in causal reasoning. So he came up with what he calls do calculus, and there are a certain set of rules, and people have shown that the set of axioms they satisfy rules such as completeness and the typical rules that are needed to make a formal operation. So in your spare time, please look up works by Julia Pearl. So he proposed do calculus way back in 1995, but then he kept getting back with his own commentary on this kind of a calculus. So there's another paper that he wrote in 2012, the do calculus thing. I've heard in several talks that more than 85% of people who claim to be practicing machine learning are not aware of causal reasoning, are not aware of do calculus. So please don't feel disturbed if you have not heard of this before. So, but please look it up, it's worth looking at. Now there is a small paradox I want to discuss which will illustrate the difference between the way we are used to looking at distributions and the difference that Julia Pearl made. So this is called Simpsons Paradox. It's not new at all. Special thanks to one of my professors at IIIT, Raghavan sir, and a dear friend Hari. So this was observed in 1899 by Pearson and later reported by Yule, and then in 50s by Simpson. So let us see what this paradox is. It's a very, very typical setting. A pharmaceutical company has come up with a drug, and they choose a population on whom they will administer the drug. Now among that population, some are males, some are females. And after administering the drug, they see how effective it has been. So here when I say C, I will mean drug is administered. Not of C means drug is not administered. E, males, not E, females. E stands for effective, not of E stands for not effective. And then you look at the recovery rate. And this here is showing among males, on the ones on whom the drug was administered, a certain number it was effective, certain other number it was not effective. And then they compute the recovery rate. Perfectly fine. Now you will repeat the same thing on females. On a certain number of females, the drug was administered. On certain number, it was not administered. A certain number, it was effective. Certain number, it was not effective. Now what I am showing in red is, when I look at males, when drug was not administered, looks like they recovered better. When I look at females, when the drug was not administered, looks like they recovered better. Right? Now what is the paradox then? There should be some contradiction. Now when I combine the two and I see on what fraction that the drug was administered, I am looking at the recovery rate. The fraction on whom the drug was not administered, I look at the recovery rate. Now do you see the paradox? So no drug is good for males, no drug is good for females, but when I put the population together, looks like drug is good for the population. Then on whom is the drug good? They are not a part of the experiment, right? So how do we explain this kind of a phenomenon? I can come up with numbers where it is totally consistent. Good on males, good on females, good on combined population. Such numbers are also possible. But such numbers are also possible where you see the reverse phenomena. How do we explain this? So to repeat, this is what the paradox was. So when I look at the entire population, effective given that the drug is administered is better than effective given that the drug was not administered. But when I look at the females, it's the reverse. When I look at the males, it's the reverse. So this is the paradox. So this is where do calculus comes. Now knowledge from the intervention. So the drug will not change the gender distribution. So that much we can agree upon, right? So Q stands for, let's say, males. So Q, given that the drug was administered, remains the same. So that distribution doesn't change. So now when I try to expand probability of E given do of C. So don't think it's a screen full. So please look at it term by term. So what have we done? We've expanded using the axiom of total probability, right? Probability of x given y is same as probability of x given yz and probability of x given y not of z, which is exactly what we have done. In the first term, we have introduced q. Second term, we have introduced not of q. Now, how does it simplify? You see probability of E given do of C. So now, I am looking at the first term, put the second term. Now, when I repeat it with do of not C, I can repeat the same expansion, right? Now, what I have in the two terms there, in the two equations is what I am seeing from the table, right? If this is the top equation, this is the bottom equation, you will see this term 1 is less than this term 2 is less than this, right? Now, when you put them together, you will see that indeed this is less than this. Now, you see that there is consistency. So please try to work it out, you will see it. So there are several other examples where you see Simpsons Paradox at work. So this is one example of the amount of exercise done by the person versus the amount of cholesterol. So what does this graph seem to show? If you do less and less exercise, you have less and less cholesterol. You do more and more exercise, you have more and more cholesterol. Right? So it defies common sense. But in reality, you break it up into age groups, you see, the more exercise you do, the lesser the cholesterol. So the behavior in the subpopulation is very different from the behavior of the entire thing. So these are some simple rules of do calculus. So the whole of causal reasoning is hinged around this. I don't want to go into the details of this, but clearly you can see there is insertion or deletion of observations, there is action observation exchange, and there is insertion deletion of actions. So I should be able to look at intervention, I should be able to express interventions in some way as there should be observation playing a role. I can't take the observation the way it is. So there are 3 levels of causal hierarchy. The simplest is the association. The example was storks, number of storks and the number of babies delivered. And then there is intervention, which is very critical in healthcare, right? The doctor needs to decide, should I intervene with this medicine? He has to decide, should I intervene with this surgery? And then there is counterfactual. What is counterfactual? I know the event the way it is now, but what if, let's say I had missed the bus? Would the story be different? So this is causal effect. That is, when do I say that X is causing Y? How does the distribution of Y change if X is indeed causing Y? So these are the questions we need to answer. And this is the counterfactual thing that I said. So what I know is currently I'm in Bangalore, but what if I were in Delhi? So how different would I be talking, or how differently would I have been breathing? So these are the counterfactual questions. So things that cannot be done in practice, you can explore using causal reasoning. So there can be experiments which you may not be able to conduct, but you can see how the situation will look like by using the counterfactual part of the causal reasoning, which I think is very, very important. So we can't conduct all possible experiments, right? So we need to have this kind of analysis. So in conclusion, causal reasoning will definitely lead to better interpretation, explainable AI, and perhaps the way ahead is curve fitting all the well-known ML techniques along with causal reasoning. Thanks. I want to thank Professor Uttam and his team for giving me this opportunity, though the talk was so much out of place. Thank you.